Dear students, welcome back again. I am going to solve some illustrative examples on fluid dynamics, which is chapter 5. Before I start these examples, I shall speak few points on the previous topics. The first one is fluid statics, which is chapter 3, which is concerned with forces which are acting on an object for a liquid at rest. We have solved many problems on this. And next to that, chapter 4, fluid kinematics, deals with the geometry of motion, space and time relationships, which means velocity and acceleration in flowing fluid, without considering the forces causing the motion. And under this topic, which is fluid dynamics, deals with the fluid flow, which is all forces that affect the phenomenon which are going to be considered. So all forces will be considered. So under this session, you have three basic governing equations for fluid dynamics. The first one is continuity equation or conservation of mass, and the second one is energy equation, and the third impulse momentum equations. So I think we will focus on these topics to solve some problems. So let us start first part 1, equation of motion, continuity, Bernoulli's equation, and discharge measurement. So we have this first example problem, fluid flow rate problem. So if you have a taxi, then you need to fill some gasoline or benzene just to run the engine. So let us see. A taxi driver is refilling at a gas station. So the fuel nozzle with diameter 2 cm delivers 20 liters of fuel in 80 seconds, assuming that the continuity principles apply. So determine the flow rate of the fuel and the velocity of the flow. So you see this is just a gas station, so you need to fill oil. It's just some fuel for your taxi. So you have nozzle. So you have diameter and also you have volume, then time. So solution, just flow rate simply, what does it mean, flow rate? The amount of fluid comes out from the nozzle in 1 second. So this is the basic definition of flow rate. So I think flow rate, it is not new for you from physics background. I hope you know this one. So I think you have formula for flow rate, which is Q, volume divided by time. So I hope using this equation we are going to solve. So we can use the formula, this formula, to solve flow rate, volume divided by time. So you have 20 liters divided by 80 seconds. So you need to get flow rate, which is just liters per second, 0.25 liters per second. So if you convert into meter cube per second, then you can find 2.5 times 10 to the power -4 meter cube per second. And from this continuity equation, you know this continuity equation, discharge area times velocity. So you can find velocity discharge divided by area. So if you divide area of the conduit or nozzle, 5/4 d square. So I think you can find this equation. Finally, 0.1989 meter per second. So this is first example for this chapter. And the second example is continuity and Bernoulli equation. So let us see. You have pipe. Water flows through the horizontal pipe shown in the figure at a rate of 0.35 meter cube per second. So if viscous effects are negligible, viscous inside the pipe, determine the water speed at section 2. At this section, what will be the speed? The speed of water. And the pressure at section 3. Section 3 means this one. Then the flow rate at section 4. So given quantities, you have diameter, pressure, and discharge. And then how do you compute? So as I said earlier, you have three basic governing equations to compute fluid flow, which is the fluid dynamics. You have continuity equation, energy equation, and impulse momentum equation. Now let us see. To compute, apply Bernoulli equation, which is energy equation between 1 and 2. Section 1 and 2. Section 1 is this one, and section 2 is this one. So how do you compute? So you have pressure P over gamma, velocity head, potential head. Pressure head, velocity head, and potential head at section 1 equal to at section 2. So since assume horizontal, just the elevation is the same, so Z1 will be cancelled out by Z2, then P1 given, P2 given. So if you substitute in this equation, just use unit weight of the fluid or water 9.81. Then if you substitute, just cancel this, then you can find here V2. V2 will be 8.85 meter per second. So this is the velocity in section 2. So from this, apply continuity equation, which means total discharge equal to area 1 times V1 equal to A2 times V2. So once you have flow rate, which is given at section 2, flow rate is given, so you can find this is 0.283. So total discharge, which is coming here, total Q is divided into Q1, Q2, Q3, Q4. So you have total discharge here. So you have here 2, Q2, Q3, Q4. So summation. So total discharge will be the summation of all branched pipes. So you can find based on this concept. So first you have discharge in section 1, which is Q1 over A1. Then you can find 3.04 meter per second. So according to Bernoulli equation, we have found already velocity 8.85 meter per second. Applying again Bernoulli equation between 1 and 3. Between 1 and 3. So assume horizontal. So you have elevation Z1 equal to Z3. So you will cancel Z1 by Z3. So the same pressure is given, velocity is given, then you can find pressure at section 3 will be computed. So according to the problem. So pressure P3 will be computed here. You have this equation. Then finally, to compute the discharge passing through this one, through this section, you can use summation. Total Q1, which is at pipe 1, will be the sum of 2, 3, 4. Pipe 2, pipes 2, pipe 2, pipes 3, and pipe 4. So from here, once you have Q1, then you can subtract Q1 from Q2 from Q3 to get Q4. So once you can subtract, then you can find this one, 0.119 meter cube per second. Okay, let us see the third example, total head of water or energy head you can find. So in a pipe 90 millimeter diameter, water is flowing with a mean velocity of 2 meters per second and at a gauge pressure of 350 kilonewton per meter square. So determine the total head if the pipe is 8 meters above the datum line. Then neglect friction loss. So the pipe is 8 meters above the datum line. So you have equation, total head of water is according to the general equation of Bernoulli. You have this equation, potential head plus velocity head plus pressure head. This is specific weight of water. So you simply, since you have Z, which is 8 meters above the datum line, if you have datum here, if this is datum, then the pipe is somewhere above this level. So you can find at any point. So if you have Z here, then you can find water is just flowing above this. So you can finalize simply for 3.88 meter. So you simply substitute in this energy equation. Okay, I think it is clear. Then the fourth example is just tapered pipe. Tapered pipe, pressure head in a tapered pipe, because cross section may vary. Here at section 1 is larger than at section 2, so what will happen? So water is flowing through a pipe having diameter 600 millimeter and 400 millimeter, both at section 1 and section 2, at the bottom and upper level. So you have intensity of pressure at the bottom end is 350 kilopascal, and the pressure at the upper end is 100 kilopascal. So you have pressure and diameter at section 1 and at section 2, and you have respective elevation, which is potential head, which is Z1 and Z2. So how do you compute? Determine the difference in datum head. If the rate of flow through the pipe is 60 liters per second, so this is rate of flow or discharge passing through this tapered pipe. Now let us solve. So as I said previously, you have continuity equation and also Bernoulli equation or energy equation. So you can find, using this continuity equation, discharge passing through this pipe is constant. A1 B1 is equal to A2 B2. Then you can finalize automatically. But you should be consistent in the units of measurement, because you have this mm and here liters per second. So convert this liters per second into meter cube per second. It will be 60 over 1000, because 1 meter cube means 1000 liter. Then you can divide by 1000, 0.06 meter cube per second. So this is the flow rate. Then if you substitute here Q over A1, you can find V1 here. Here is V1. Then 0.212 meter per second, and velocity V2 will be automatically, you can find Q over A2 0.477 meter per second. So the flow velocity passing through section 1 and section 2, once you know this, you can find the other parameters, which is just the elevation difference. So applying Bernoulli equation, which is energy equation, at section 1 and at section 2, we get P1 over specific weight at section 1, V1 square over 2G plus Z1, the same. So pressure head, velocity head, potential head. So if you equate both, you can find the difference. So all known values will be entered. Then you can rearrange the equation. Z2 minus Z1 will give you this equation. So this is the elevation difference between section 1 and section 2, which is 25.47 meters. This is the answer. Now, if you are asked pressure head at section 1, which means pressure 1 over specific weight. So you can find 35.678 meters. The same is true for head 2, which is P2 over gamma. Then you can find 10.194 meters. So these are the answers. So next example is example 5.5 Siphon. So sometimes water may flow out by siphoning action. So if you have hose pipe, you can take out water to the lower elevation. So by siphoning action. So let us see. A pipe of 8 centimeter diameter is working as a siphon. Find the velocity and discharge and absolute pressure at B, this point, at this point. If the atmospheric pressure is equivalent to 10 meters of water, this is head of water, atmospheric pressure at section A. So this hose is going out to this point C. So elevation difference between water level, reservoir level, and point B, 2 meters. Then again down 4 meters to C. So what will be the result? Let us see. So according to Bernoulli equation between A and C, you can take A and C. So you have pressure head at A, velocity head at A, then potential head at A. So you will consider datum above some reference point, then we will consider. So the same pressure C at this point at C divided by gamma, velocity head, then potential head. So take out elevation difference, ZA minus ZC. ZA minus ZC. So you have already the difference between A and C. If you take datum at this point, difference at this level, if you take level, then you can find VC square over 2G. Why pressure at A is 0? Why pressure at C is 0? Since it is open to the atmosphere, pressure is 0. But we will consider the other issues. So velocity at C, which is water is flowing out through this, will be 8.86 meter per second. Then once you found this one, so you have just neglect losses, then velocity at B is equal to velocity at C. So once you have flow velocity, it will go out like this. So area times velocity at B, area is pi over 4 d square times velocity. You can find discharge at B, which is 0.044 meter cube per second. Again, Bernoulli equation between A and B, you can find the same pressure head at A, velocity head, potential head, equal to pressure head at B, velocity head, and potential head. Then all values are 0. Then you can substitute the result. Then you can find pressure at B over gamma, which is negative 6 meter, which is vacuum. So why you get this one? Because already you have already 10 meters of water already given. At point B, you have atmospheric pressure is equivalent, absolute pressure at B is given already. So find the velocity, flow, discharge, and absolute pressure at point B, which is this point. Then you can substitute. Then finally, it is vacuum. Negative sign is vacuum. So vacuum is considered. So vacuum will be included. So this is as exercise. You have plastic smooth siphon. So just to irrigate some blood using this, find the flow rate from the pool of this water to 0.3 meter down or below the bottom of the tank. So you can try this one. And the other example is tank flow rate. Tank flow rate, we will see. I think this is example 5.6. It will be example 5.6. Okay, I will proceed the same. Okay, so this is all about today's tutorial. Hopefully you liked the video. And thanks for watching.